So what we discovered is that to power the sun requires a source of energy that we have not discussed yet. It is not electromagnetic energy in the internal structure of an atom. It is not gravitational energy. Where else can you mine potential energy? This was a puzzle until the 20th century, and the answer, of course, is nuclear energy. And so we'll have to learn a little bit about the structure of the nucleus. And we talked, when we mentioned the nucleus and its construction out of protons that are positive and neutrons that are neutral, that there's a big puzzle. That's a collection of positive charge without any negative charge, and there's a very strong electrostatic repulsion between all these charges. Remember, electric forces, like gravitational forces, decay with distance, like 1 over r squared. These are the forces at distances of 10 to the minus 15 meters, the size of a nucleus. These protons are very close up against each other. There's a huge repulsive force between them. But nuclei don't fall apart. Something must hold them together, so it's natural to conjecture, and later to verify, the existence of a very strong attractive force that binds the nucleons to each other and overcomes this electrostatic repulsion. How strong is the force? Well, strong enough to overcome the electrostatic repulsion between protons in a nucleus, and that's a very strong force indeed. On the other hand, we know that this force cannot extend beyond the confines of the nucleus too far, because if it did, then the nuclei of 2 neighboring atoms would attract each other and collapse on top of each other. And so, unlike gravitation and electromagnetic interactions that are long-range interactions, volumes interact, every part of the universe attracts every other part gravitationally, the nuclear force is a short-range force. At ranges larger than the size of a nucleus, it effectively decreases to 0. And so there's no interaction between neighboring nuclei. We don't have a problem. We have this very strong force. And this brings up the idea that maybe just as rearranging electrons led to the liberation of electrostatic potential energy, maybe rearranging nucleons inside a nucleus can liberate nuclear energy. And we've learned a lot about nuclear energy. The way to parameterize the amount of potential energy liberated in creating a nucleus, similar to the way we computed the gravitational energy liberated in creating the sun, is to say, imagine starting with a bunch of nucleons, put them together. Of course, you'll have to input a lot of energy to get them close to each other, because at large distances the electrostatic repulsion will dominate. But once they get close, there's a strong attractive force. They'll crash into each other and liberate a lot of energy, producing a nucleus. The question we want to ask is, if you have a whole bunch of nucleons, what's the most efficient way to pack them together? To do that, we measure the total liberated energy. Nuclear minus electrostatic, the total difference, the total energy gained by constructing nuclei out of a bunch of nucleons, and we want to do that energy per nucleon, so that if you have some fixed number of nucleons, what's the most efficient way to pack them? And one would think that because we have this very strong attractive interaction, then certainly a hydrogen atom is not a good way to produce an efficient packing. A hydrogen atom is a proton. It's not interacting with anybody. It hasn't liberated any potential energy. But one would think that very heavy elements like uranium, big nuclei where there's a lot of nuclear interactions, would be the ones that liberate the most energy. And what this plot shows us, we have here atomic number, or number of nucleons, mass number running to the right, and the average energy liberated per nucleon going up, and we see that the most stable configuration is not a bunch of uranium nuclei, but a bunch, as many as you have nucleons for, of iron nuclei, the sort of intermediate range. Intermediate-sized nucleus is the most efficient packing. And the explanation for this is an important one. The explanation for this is very close to the discussion we had of the crossover between short-range chemical forces that are short-range but very strong and act on the surface, and long-range gravitational forces at about a size of a kilometer in the solar system. A similar thing happens with nuclei. What goes on is that if you have a great big uranium nucleus, then a proton that is located on this side of the nucleus and a proton on that side of the nucleus basically are too far apart to really interact through the strong force, so they do not attract each other. Remember, the attraction falls to zero. In some sense, each of these protons on the edge of a very large uranium nucleus interacts only with his neighbors. What that means, on the other hand, the electric forces between these protons decay only as the distance squared. Those are long-range forces, so these guys definitely do repel each other through electrostatic forces, and therefore the sort of efficient way to arrange the energy, just as we saw, this is really analogous to the discussion of what holds a mountain together, is to cleave this nucleus in two, perhaps. We now have lost all the nuclear energy that was involved in the bonds along the place we cut, but when these two positive subnuclei are created, they are two positive charges very near each other, they repel with a great electrostatic repulsion. That produces a lot of energy as they accelerate away, and the net result is a gain in energy. And so what we see indeed is that the most efficient way to pack is iron, and nuclei heavier than iron are not efficient packing, and by rearranging their nucleons, they can liberate energy. Well-known case is the case of fission. This is the case exactly where this nucleus of californium breaks into cadmium and tin and some debris, some extra neutrons flying around, and in the process liberates essentially the electrostatic repulsion that once these two nuclei are free, they are repelled and proceed at great energy to move away from each other. Another popular mode of breaking up if you're a heavy nucleus, we see here seborgium emitting an alpha particle. Remember, an alpha particle is just a helium nucleus, 2 protons and 2 neutrons, and the seborgium decays to rutherfordium. So both of those modes occur in heavy nuclei. They liberate a lot of energy. This was the radioactive energy that heated up the interior of Earth. Remember, that was the 89 watts per meter squared or 87 watts per meter squared that were bubbling up from nuclear reactions in the core. But it's not going to be enough to power the sun, because in the sun we don't have rutherfordium or californium or uranium. We have hydrogen. And hydrogen, remember, is way on the other side of the divide. Hydrogen atom nucleus is just a proton. It's not bound to anything. Of course, if we could make bound states of protons, maybe we could gain, but there are no bound states of protons only. Helium-2 is not a stable nucleus. If you put 2 protons together, they may bind for a short time, but the electrostatic repulsion will break that nucleus apart very quickly. And so the first really stable nucleus, and it's a very stable nucleus indeed, is helium-4, that alpha particle. If you can make a helium nucleus out of the hydrogen, you will have gained all this energy. That's very good. The problem is that to make a helium nucleus, you need 2 protons, 2 neutrons. The sun is full of protons, but there's no neutrons, essentially. Where do you get the neutrons? We can't, using the strong force, convert protons to neutrons, but we know that somebody can. And the reason we know that somebody can is because we talked about beta decay of nuclei, and we see here sort of the decay of fluorine to oxygen. And what's going on here is, since this is a positive beta decay, you can look at the atomic number and see that, in fact, one of the protons in the fluorine is being converted to a neutron. So fluorine is decaying to oxygen with the emission of a positron. And there's also the inverse reaction, in which here carbon-14 converts one of its neutrons to a proton, becomes nitrogen-14, and emits an electron. And so we know about these decays. In fact, a free neutron decays to a proton within about 15 or 16 minutes. And so there is this thing called the weak nuclear force, probably better called the weak interaction, which mediates these decays. It is possible for one elementary particle to be converted to another elementary particle. And this is a very confusing thing, so we have to sort of stop. We're not going to discuss the physics of the weak interactions, fascinating though it is, in detail, but we need to set some ground rules. So, what is this? Can a force magically convert one particle into each other? We understand that a force can cause a rearrangement of the constituents of a particle. So one could imagine maybe that a neutron is really just a very, very tiny hydrogen atom. There already were a proton and an electron inside the neutron, and then they just fell apart. The answer is no. It's a very bad idea to think of a neutron as a hydrogen atom. There was no proton inside the neutron. The neutron honestly decayed to a proton and an electron. And yes, the weak interactions can change one particle to another, but there are going to be some rules that we need to understand. And then there was this third object there. It's called an anti-electron neutrino. So the Greek letter nu stands for neutrino. The bar says anti, and the subscript E makes it an electron neutrino. And what all that means, we'll have to understand. So let's set the rules. What can interactions do? What can they not do? They can't do anything they want. The rules, basically, it turns out, are restricted to our good old-fashioned conservation laws. That's why we made such a big deal about them when we were learning. Now, there's a tricky business here. We're stepping into the beginnings of relativity when you allow particles to decay. We will spend almost an entire week understanding relativity later in the class. For now, I'll just say the words. We had in Newtonian physics a conservation of energy and, of course, conservation of mass. In relativistic theories, those are combined in the conservation of the sum of energy and mass. Mass is a form of energy. There's the famous conversion ratio, the square of the speed of light. We will talk about this. It is not that relevant to the processes that take place in the sun, despite what you may have heard. And so when it's important, we will talk about relativistic physics. But mass and energy are conserved. Momentum is conserved, just as it always was. Angular momentum is conserved. If you're dealing with elementary particles, you need to remember that elementary particles carry intrinsic angular momentum. It's called spin. You could imagine that a proton always spins, and this rotation is at a constant rate and points in some particular direction. And then there are the other kinds of conserved quantities that are not to do with motion. We talked about electric charge. Electric charge is conserved. No matter what processes go on, the total electric charge in any region of the universe doesn't change unless charge is flowing in or out. And then there's a new one that we discover as we start to develop particle mechanics, and that is a property called electron number. An electron carries electron number. A proton, obviously, has 0 electron number, as does a neutron. An electron number we'll see is conserved, and this restricts what can happen in interactions involving electrons. And the interactions we're going to study are the weak interactions. What makes them weak? We said they're not really a force. They are things that happen. The strength of the interaction essentially measures how frequently a reaction will happen. Weak interactions occur very slowly. They are rare. One out of many, many attempts will generate a reaction. The example is the neutron that survives as a free particle for 15 minutes. By particle standards, that's a very long time. So, who are the players? Well, here's a list. We're into particle physics now, of all of the particles we have, or should be discussing. And they include, well, I'll start at the bottom. We have our friend, the photon, denoted by gamma, hence gamma rays. And I've written the quantities of their conserved charges. Of course, their momenta and energy depend which way they're moving, but a photon is a neutral particle. It carries no electric charge. It is not an electron, carries 0 electron number. And then here we have our proton, neutron, and electron with their known electric charges and with the fact that the electron carries a charge not carried by any of the others. And then there's this other interesting object. It's called a neutrino. And the neutrino was discovered because when neutrons decayed, studying the conservation of energy mass, it was discovered there was missing energy. It was the idea of Wolfgang Pauli to think that maybe there was a neutral particle that doesn't interact with anything, that is not detected by any of our detectors, sails right through the detectors, and produces and carries off the remaining energy. Since it was electrically neutral and didn't interact with anything, it was called a neutrino. We now know that these particles exist, and indeed are part of this. And in fact, an electron neutrino carries electron charge, electron number 1. And this will become important in what follows because the weak interactions of electrons and protons conserve electron number. What that means, in particular, is that when a reaction occurs, we need to balance all of these quantum numbers. They're all conserved. So, for example, the decay of a neutron into a proton plus an electron conserves electric charge because the neutron is neutral and the total electric charge of the products is 0. But it does not conserve electron number. Electron number was magically created. And indeed, this means that if you have a neutrino and a neutron, and they react, that can produce a proton and an electron. Now, I was about to write something on the right-hand side because, of course, a free neutron decays without anything hitting it. This brings up the fact that there's this whole bottom line of the table, and it turns out to be another important principle of physics, that for every particle there is an antiparticle. An antiparticle is not something mystical or mysterious or a particle moving backwards. It's simply another kind of particle which has the same mass as the original and all the opposite charges. So, for example, there is an antiproton, which has the same mass as a proton, but is negatively charged and, of course, carries the same zero electron charge. There is an antineutron, which is neutral. There are anti-electrons. They're called positrons. That was what was emitted in positive beta decay. They carry the same mass as an electron, but electric charge positive and negative electron number charge. And the neutrino has its own antiparticle, and the anti-electron neutrino is neutral, like the electron neutrino, but has the opposite sign of electron charge, and so the decay can proceed if an anti-electron neutrino is produced over here. This conserves all the charges. Now, these neutrini are very hard to understand. They interact only through this weak interaction, which, as I said, makes for rare events. So mostly they don't interact at all. In the time I've been talking about this slide, some millions of neutrinos have penetrated each and every of your fingernails. You have not felt them because they don't interact with anything. In fact, the great majority of them will sail right through the Earth and come out the other end and keep going through the universe. They carry very little mass, if any. In fact, they were for a long time thought to be massless. And they don't interact, which makes detecting them a very difficult proposition, as we will see. But they're important because they balance the charges in weak decays, and as we'll see, they have some other important role in our story. I didn't bring them up just to tell you about particle decay. And there's the property that if you take a particle and an antiparticle, say an electron and a positron, that combination has total charge 0 with respect to all the conserved charges except for energy and momentum. And so if you bring an electron and a positron near each other and they're at rest, there's just energy, that's in their mass, and that indeed can be converted to straight radiation. The electron and the positron annihilate, and a burst of gamma radiation flies off in both directions, and the energy is essentially the mass of the disappearing electrons. This is a process that does occur, and we will have to understand how that happens, as I said, when we talk about relativity. For now, we recognize that if you have an electron and a positron, you can liberate energy. This also explains why we don't see antiprotons or positrons in day-to-day life, or anti-hydrogen atoms that you could make by binding a positron to an antiproton. The reason is that living in a world as we do, which is saturated with electrons, a positron, for example, has no chance. A positron will electrically attract neighboring electrons, of which there are many, annihilate, and so positrons do not survive in our universe. We'll come back to the discussion of why there are protons and no antiprotons in our universe much later in the class. For now, I just wanted to, having brought up all these particles, to explain why we haven't seen them.